Okay, so now we get to talk about heat and physical transitions. And just to remind you, we talked about this at the very beginning of the course. I'm going to bring it back again, and this time we're going to introduce the idea of heat. All right, so you may remember that when we plot pressure versus temperature for any given substance, ultimately we obtain a graph that gives us boundaries between the solid, the liquid, and the gas. The sublimation point, the melting point, and the boiling points, right? So um, we've talked about the distribution of the solids and liquids being at higher pressures than gases, the gases and liquids being generally at higher temperatures than the solids. We talked about that. But what we haven't talked about is what happens in terms of energy input or output when we undergo the transitions themselves. And we can do various number of transitions. We can go from solid to liquid. We could go from solid to liquid to gas, or we could go directly from solid to gas. And in other circumstances, we can go just from liquid to gas, right? So those are all the circumstances in which we actually increase temperature. And because we're increasing temperature when undergoing those transitions, the amount of heat is going to be positive, meaning that the substances will have to absorb heat in order to undergo the transition. All right, now we're going to focus on a simple one for the time being. We're going to look at the solid to liquid transition. So we're going to go from a solid down to liquid. In order to make that happen, we have to start from a temperature below the melting point and end up at a temperature above the melting point. All right, so that's what we're going to be going after. And although the initial pressure temperature graph is nice and conveys the idea, there's a better graph that will help you depict all the different processes that you have to account for. Now, the way this works out is that you create a new 2D plot, temperature versus energy, temperature now on the y-axis. And what you want to do is that for the specific substance in question, you want to have a plotted horizontal line at the specific melting point and boiling point of the substance. In this case, I'm only concerned with the boiling point because I'm only going to go slightly above the melting point. But usually you want to have horizontal lines segmented as shown here for the melting point and the boiling point of the substance. The fact that this is 0 degrees Celsius means that we're looking at the melting point of water. All right, now, if you're going to be a solid, that means that you have to be below the melting point. So you're going to be somewhere down here as far as your initial temperature. So you're going to be definitely below. And what's going to happen is that you're going to start heating up the substance until you reach the melting point. Now, the process of heating up the substance while it still is a solid, which is what has to happen because you're below the melting point, is simply determined by Q. Q equals mcat. But the moment you hit the line over here, what ends up happening is that now you are undergoing the process of melting the substance. And when you hit this horizontal line, what you basically do is just kind of like boulder out to some extent. And this horizontal bold line now represents the process of melting the substance. So we're going from ice water to liquid water, but it's the process of the ice water turning into liquid. Okay, so you still have some ice, you still have some liquid, you're still melting. But notice that because this is horizontal, the temperature remains constant. At the melting point, as long as you have some ice left in there, the temperature will remain 0 degrees Celsius. It will not change. But the very moment that all your ice has turned into water, if you have any residual energy present, now that energy will be used to raise the energy of all of the water that's now present in the liquid form. And notice now that we go up in slope because we're increasing the temperature. So here we have three different sets of data. We're going from the solid to the liquid. So first we're heating up the solid. That's step one. Then we melt the solid. That's crossing the boundary right here. And we end up generating the liquid, which is the third step. All right, now in terms of the equations, this is where a slightly new way of thinking comes in hand. First of all, The Q's where the temperatures are changing, so Q1 and Q3, can be given by MCAT. But the heat capacity has to be now the heat capacity of the corresponding state of the substance. So if we are below the melting point, this has to be the heat capacity of the solid, represented by little s. If we are above the melting point, but below the boiling point, this has to be the heat capacity of the liquid. And it's very important that you pick the right heat capacity for the corresponding state, because these numbers are not the same. And in some circumstances, they can be, twice as large as each other. So you could end up with some really messed up calculations if you end up messing up the order. So just be sure that solids are associated with below the melting point, liquids with the in-between boiling point and melting point temperatures, and gases with temperatures above the boiling point of the gas. But other than that, as long as the temperature changes, you use MCAT, the mass of the substance times the specific heat of the substance times the change in temperature. That will be true for Q1 and Q3. But for Q2, where the temperature remains constant, you can use MCAT because the change in temperature is zero, right? That will just vanish away. So instead what you do is you use an enthalpy value, an enthalpy that's in kilojoules per mole. So instead of multiplying by mass, you will multiply by the moles of the substance. And for the melting point, you will specifically use the enthalpy of fusion. Fusion is synonymous with melting. So it's technically synonymous with freezing, but that's besides the point. The enthalpy of fusion you want to associate with the melting point of the substance. So in this flat region, you definitely want to use enthalpy and the moles. All right, now in terms of the change in temperature for Q1 and Q3, you gotta pay attention to where you start the graph and where you're ending the section, right? So you start initially at this lower temperature, Ti, red Ti, and you're gonna end up at the melting point temperature. That's your T final. At the same time, that's the initial temperature where the liquid starts rising up in temperature. So the T initial is also 0 degrees Celsius for the liquid, and the final temperature of the liquid is wherever you end up in the process. So to give you a concrete example, the way this will actually read in a typical problem will be as follows. I will ask you how much heat is required to melt a given amount of the substance, so 18.02 grams of ice, from -5 to 37 degrees Celsius. And I'm giving you the heat capacity of the solid, 2.064, the heat capacity of the liquid, 4.184, and the enthalpy of fusion, 6.01. Alright, so now what you want to do, technically speaking, is draw this graph, because this is what you will see first, the information. What you want to do is draw the graph, and the first thing you do is draw the horizontal segmented line for the melting point and the boiling points of the substance. Then you locate your T initial and your T final based on the question, based on the information in the question, and with that info, you simply want to go from T initial to T final, and if you happen to cross the horizontal line in order to go to T final, that's where you're going to end up breaking this into different processes, in this case 3 processes. So what that means is that for Q1, we have the mass of 18.2 grams of ice. We have the heat capacity of solid water, which is the ice, so 2.064, and a change in temperature, which is final 0 degrees minus -5, right? So we have 0 minus -5, which is the same thing as 0 plus 5. All right, now similarly, for Q3, we have 18.2 grams of water, still the same thing. The heat capacity of water, 4.184 joules gram degree Celsius, and then change in temperature, which is 0 degrees Celsius initial, 37 degrees Celsius final, right? So we have 37 minus 0. And for Q2, the flat region, the enthalpy of fusion is 6.01 kilojoules per mole. What you have to do is convert the 18.0 grams of water to moles. And in order to do that, you use the molar mass. So here I just so happen to use specifically the mass of water that will give me 1 mole, but in other problems the number of moles will change, so be cautious with that. Don't assume that this is 1 mole automatically. Alright, so at this point what you do is you multiply the numbers. So 0 plus 5 is 5, multiplied by 2.064, multiplied by 18.02. 37 minus 0 is 37, multiplied by 4.184, multiplied by 18.02. And you're going to find out that Q1 is 186 joules, Q3 is 2790 joules, and Q2 is 6.01 kilojoules. The second to last thing to do is to change the units of kilojoules to joules so that everything is in the same unit. So you multiply by 1,000. And at this point, since you're interested in finding out the total amount of heat, you want to add up all three of these values to give you your total, which actually should be closer to 8,000. So this is a little typo. My apologies. It should be closer to 8,000. But the idea is this. Yes, you will add all of these energies together for the individual processes, and you want to make sure that all the units are the same. All right, I'm going to give you one more example for the phase transition diagrams. It's a similar procedure, a little bit more complex, so I'm going to save that example for the next video, but after that we'll be done with the phase transition. So let's stop right here and we'll reconvene on the next video.